Hello and welcome to CMG's webinar on the role of coupled geomechanical modeling in reservoir simulation. My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'll be the moderator for today's session. I'm pleased to introduce Varun Pathak, Senior Reservoir Simulation Engineer at CMG, who will be presenting today's webinar. Varun has over 8 years of industry experience and specializes in fractured carbonate reservoirs, geomechanics, and unconventional reservoir simulation, specifically for shale, tight oil, and gas reservoirs. He holds a bachelor's and a master's degree in petroleum engineering from the Indian School of Mines and University of Alberta, respectively.
Thanks for the introduction, Anjani, and thanks everyone else for joining in and listening to our presentation on the role of coupled geomechanical modeling in reservoir simulation. Today, my agenda would be to introduce geomechanics to you for those of you who have not seen geomechanical modeling in numerical simulations. I'll introduce you to the concept of deformable reservoir as well. We'll look at the applications and the needs of geomechanical modeling after that, and then I'll cover some basic theoretical concepts so that we can set the stage for the more advanced features to come later in the presentation. We'll look at how geomechanical modeling is done in CMG software, including the various ways the coupling of flow in geomechanics is done, the dual grid system, and geomechanical post-processing feature. And then we'll see a demo on how to actually do that in the software. Finally, I'll talk about 3 case studies which we presented at various SP conferences in the past few years. So let's start off with an introduction to geomechanics. Geomechanics is the geological study of the behavior of soil and rock. And when you inject something into the soil and rock, the behavior will change. There are 3 pictures at the bottom here, and you can see on the left-hand side, the first picture, it shows you what happened when people started producing water from an aquifer just below the ground where the man is standing here. This picture is from California. In 50 years, the ground subsided by about 6 meters, as you can see. And you can imagine the impact that would have on any surface equipment that you have, or any well equipment that you have there. In the middle picture, it's from Las Vegas Valley. Once again, the water being pumped from the aquifer for daily usage. And once again, you see the ground has subsided there, rendering the surface equipment useless. The right-hand side picture shows you an actual oil field operation in the North Sea. The platform was the famous Ekofisk platform, which sank quite a bit in just a few years because of oil and gas operations. And that posed a risk to the platform itself and the people working on it. So geomechanical effects can be really, really significant depending upon what process you are doing and which field you are working in. And we need to understand their effects and try and do some modeling work to try and mitigate the risk which we can pose by doing oil and gas operations. Conventionally, the reservoir engineers have been using non-deformable reservoirs. In non-deformable reservoirs, the pore volume can still change, but the bulk volume stays constant, which means the grid block shapes will stay constant no matter what. And the example here is from a producer well, which produces from a reservoir, and the reservoir shape does not change. Even in these models, we always use a basic geomechanical features without even realizing about it, and that feature is rock compressibility. So we always have rock compressibility, which ends up changing the pore volume of the rock based on the pressure. Sometimes we also use compaction tables, and sometimes we use Karman-Kozeny formula, and sometimes, especially in thermal simulations, we use dilation models. So all these different models try and mimic your geomechanical features to some extent. But the real geomechanical modeling incorporates the feature of deformable reservoir. In deformable reservoir, the pore volume can change, and the bulk volume can change as well, which means the grid block shape can change, and which is what you see happening in this video in this slide. So here we have a producer and an injector because it's a cyclic steam simulation. Because of the operation of this well, what happens is the ground subsides, and the grid block shapes are changing, as you can see now. Another example of deformable reservoir. On the left side, there is a producer well in a simple reservoir, which causes subsidence of the reservoir, which means the top of the reservoir sinks in. On the right-hand side, we have an example from steam-assisted gravity drainage, where we are injecting steam at a high pressure and temperature. And in this case, you can see that the top of the reservoir is actually rising up, and that's called heaving. And in both these cases, you can see that the grid block shapes have changed with time. So why do we need geomechanical modeling? Well, we saw some examples before, but just to enlist everything here, on a well scale, it can help you answer questions about wellbore stability, sand production, and the propagation of hydraulic fractures, amongst other things. On a field scale, you can answer questions about fault activation and reactivation. You can predict subsidence and heave of your reservoir. You can ensure there is Caprock integrity that is maintained. You can find out the effects of geomechanics on different reservoir flow properties like porosity and permeability. And you can also use geomechanics to assist you in doing 4D seismic history matching. We'll look at some of these things in our case studies later on. But before we go on further, let me introduce some basic concepts. You might remember some of these things from your undergraduate days, but just to set the stage properly. Stress is just the ratio of a force acting on a surface to the area of that surface. And stress can have directions. So in the left-hand side bottom picture, you can see there is a three-dimensional body, and there is a bunch of stresses acting on that. Some stresses are acting perpendicular to the body, and some stresses are acting on the surface. The perpendicular stresses are called normal stresses, and the superficial or surface stresses are called shear stresses. And all of them can be represented in one big stress tensor. So this is a tensor. The diagonal elements are your normal stresses, and all other elements are the different shear stresses. And of course, you need to solve for each of these when you do a geomechanical simulation. Then we come to the concept of strain. Strain measures how much overall deformation a body has undergone when some forces act on it. So initially, there is a body which is shown in the blue color there. When you when you put some forces on it, that changes the position of the body, and it changes the shape of the body. And a combination of both these things is the overall strain. And just like stress, the strains are also normal or shear, and they are also represented in that big tensor on the right-hand side bottom. And then there is a concept of effective stress. Effective stress is the average normal force per unit area transmitted from grain to grain of your rock. So your rock, which is buried deep into the reservoir, will be acted upon by the overburden stresses. Now these stresses have to balance somehow. And what balances these stress is the pore pressure inside your rock and the effective stress acting on your rock grains. So the right-hand side equation shows you that total stress is effective stress plus alpha times pressure, where alpha is the Biot's coefficient. The I you see is the identity matrix. And just to review the basic equations, this is one of the couple of slides where we have equations. The first equation on this slide shows you the force balance equation. So it's a combination of all the stresses and all the forces that act on a body. The overall resultant is 0 at any given time because the body is in equilibrium. So that's the first equation. The second equation relates the strain to the overall displacement. The third equation relates the stresses to the strains. The third equation, there's a term called C that's called the tangential stiffness tensor. So it's something similar to Young's modulus, but Young's modulus is applied in 1 dimensions, and the tangential stiffness tensor is applied to 3D. You can also see that this equation has terms of pressure and temperature. So that's the most basic poroelasticity equation. Now how do we solve these equations? So Cmg Solution Outline is on this particular slide. If you combine all the equations from the previous slide, you'll get the first equation on this one. So that is the equation which comprises of everything, the forces, the displacement, and everything. We use the first equation, and we figure out how much the applied force is, and based on that, we figure out what the displacements are. Now, once we know the displacement, we can use the equation number 2, which is same as the one on the previous slide, to obtain the overall strain tensor. Once we have that, then we can apply the relationship between stress and strain to get the effective stress tensor, and that's how the solution works. So we go from left to right in CMG software. It's perfectly fine to go from right to left as well, but the R&D department at CMG found that going from left to right, as shown on this picture, was a more effective way and faster way to solve the equations. Now, what does the coupling of geomechanics and flow simulation mean? What happens when you solve flow equations? You are solving a bunch of equations like material balance, phase equilibrium, energy balance, volume constraint. And these equations give you the solutions for pressure, temperature, and so on. Geomechanics equation on the other side use these pressures and temperatures to calculate displacement, strains, and stresses. So geomechanics needs to obtain the values of pressure, temperature from flow equations. In turn, geomechanics will calculate the change in porosity, which is given on this slide in this equation. So porosity at any given time step is equal to porosity at the previous time step, plus the effect of pressure, plus the effect of temperature, plus the effect of stresses. So just like geomechanics needs to know some information from reservoir side, sometimes reservoir may also need to know some information from geomechanics side. So these two have to have some communication between each other, and that communication is called coupling. Types of coupling are basically two main types of coupling. You can couple in a fully coupled approach, in which we will solve all the equations and everything in one big Jacobian matrix. Or the second way is to go and do an iterative coupled approach, which is what we do in CMG. We found that the second approach was quicker and just as efficient as the fully coupled approach. The iterative coupling approach is shown on this flowchart. So you start off with taking a time step and computing the pressure and temperature in the reservoir simulator using stars or gem. You use these values to compute the displacements, stresses, and strains in the geomechanics module of stars or gem. And based on that, you can compute the changes in porosity and permeability. Now you have two options. Either you want a coupling iteration or you don't. When you don't want the coupling iteration, which is what you do when you choose option no here, you are using an option called one-way coupling. And you go and take the next time step. So basically you have communication from reservoir simulation to geomechanics, but no communication between geomechanics and reservoir simulator. So you transfer pressure temperature from reservoir to geomechanics, but not the porosity from geomechanics to reservoir. Now if you use the coupling iteration option, which is the option when you use yes, then it's called a two-way coupling. In this case, the updated porosity and permeability will be fed back to the reservoir simulator, which will have to calculate the pressure and temperature again, which will then lead to an updated value of displacement, stresses, and strain. And we go on this loop on the right-hand side until we reach convergence. And once we reach convergence, we go and take the next time step. So that's how these two couplings work. Two-way coupling, as you can see, it requires a lot more calculation, so it can increase your runtime quite a bit. One-way coupling is faster. But sometimes you do need two-way coupling. How to figure that out? You should run your simulations first with one-way coupling and see how big the geomechanical effects are. If they are big enough, then you go and do the two-way coupling. So that's our recommended approach. Now, before you set up any coupled geomechanical study, you need to ask yourself some questions about the inputs. Do you have knowledge of geomechanical rock types or not? You need to know the distribution of rock types in your reservoir, as well as their individual material properties, like Young's modulus, Poisson's ratio, cohesion, and so on. You need to know what constitutive model you need to use for your rock, and maybe different rocks can have different constitutive models. We have all the options available in CMG software, but you need to choose the correct ones for your field. You also need to know the initial stresses. Just like you know your initial pressures for reservoir simulations, you need to know initial stresses for geomechanics simulation. And you need to know permeability dependence on geomechanics, and in some cases you may need more information. So these are the basic information that you need to know before you can set up a geomechanical study. Before we go on further and I show you a demo, I also want to tell you about the dual grid system. This is one of the advanced features of CMG software, and what it lets you do, it lets you choose your reservoir grid as refined or as coarse as you want, and you are able to superimpose a dual grid on top of the reservoir grid. Conventionally, when you do geomechanical simulations, what the software's different software, what they do is they make a copy of your reservoir simulation grid and solve this copy in finite element method. Now that has some limitations. For example, if your reservoir is 2 kilometers deep and you want to know what is happening at the surface, you need to extend your reservoir grid all the way to the surface and increase your number of grid blocks to a huge extent. Dual grid system overcomes this limitation. It lets you add a geomechanics grid completely independent of your reservoir. So what happens is you have a reservoir grid which is just like you would do without geomechanics, and you create a second grid system which covers the length and breadth of the reservoir grid and goes beyond that. And it is extended all the way to the surface in this example shown by the black lines. And by doing that, you can represent the whole overburden, underburden, side burden, and a big area using a very few grid blocks. And that's a very, very good approach, because sometimes we need to know what happens far away from the reservoir, and we don't want to solve millions and millions of grid blocks. In 2D, the picture is shown on the right-hand side. So you can see the reservoir is deep, and this is the reservoir, and you have very coarse geomechanical grid blocks extending all the way to the surface. In the reservoir section, the geomechanical grid blocks are refined. This dual grid system works on the concept of mapping. So you map pressures and temperatures from reservoir to geomechanics, and you map the updated porosities and permeability from geomechanics to the reservoir grid. So in this slide, the dashed lines are the geomechanical finite elements, and the solid lines are the reservoir grid blocks. So properties are mapped from each grid block to its corresponding geomechanical finite element. And the mapping is done based on inverse distance based interpolation. The formulas are on the right hand side, and we go over them in great detail in our training class, so I'll encourage you to attend that as well. The advantages of using dual grid system is that geomechanics and reservoir grids are completely independent of each other, and you can model overburden, underburden, side burden without adding too many grid blocks. Another advantage is that you can use any grid system you want in the reservoir. You can have local grid refinements or faults. And geomechanical grid can be of different sizes in different areas of the reservoir, and you can use corner point grid as well. The computation time is less because you are using less number of grid blocks, and you can plot the results from both the grids, from reservoir as well as geomechanics grid, in results 3D and results graph. So with that, I'll go to the demo, but before I do my demo, I want to introduce you to the concept of steam-assisted gravity drainage, because the demo example talks about this process. So SAGD is a process which we use very commonly in Canada to extract very heavy oil and bitumen from the reservoirs. So what you do in this particular case is you drill two wells, two horizontal wells. One of them is injector, which is the top one, and one is a producer, which is the bottom one. From the injector, you inject steam, and steam rises up because of gravity differences, and it heats up the oil. Oil becomes mobile, and it flows down to the producer and gets produced. So that will be my example in the demo. So I have a simple case. It's heterogeneous reservoir with one SAGD well pair, so one injector and one producer. I'm showing you the distribution of porosity in the reservoir. This reservoir is 500 meters deep, as you can see, which is considered deep from SAGD standards. And you can see that a bunch of properties are finished here on the right-hand side, on the left-hand side. And I have some geomechanical properties that I have added here. So let's look at what I have added. So when you see geomechanics, you can see that there is two options for finite elements. You can use 2D or 3D. I'm using a 3D option here. Then there is an option for coupling. The number is 2. There is other options. You can choose the numbers 0, 1, 2, and 3. The number 0 stands for one-way coupling, which you saw in a couple of slides earlier. And the numbers 1, 2, and 3 are all two-way couplings. Different kinds of formulas to calculate porosity in each of these numbers, though. The other settings are all numerical settings. So we leave all of them as default. The next thing you need to specify is the data of geomechanical rock types. So I've done that as well here. I've set up one geomechanical rock type. You can choose any model you want to use for this rock type. I'm using the Moore-Coulomb model, but there's a bunch of other models which are available for your use as well. Moore-Coulomb is the simplest one, and it's generally the one which is used a lot. But you can use any of the other ones if your reservoir shows the behavior of those other ones. In addition to what you see in Builder, there are more models available through TextPad. They have not been put into Builder yet, though. So what you need to enter is the value of Young's modulus. I've entered it here. Poisson's ratio. I have a data for cohesion as well, so I entered that, and the data for thermal expansion coefficient. And that's it. My geomechanics is all set up, except I'm missing the data for initial stresses. I cannot enter the initial stress data in Builder, so I'll do that in TextPad. And I've already done that in this example. So I've set up two keywords, stress 3D and stress gradient 3D, and I've input the values for them. Both of them have 6 numbers. The first 3 numbers set up the values for normal stresses, and the last 3 numbers set up the values for shear stresses. And I'm assuming that shear stresses are 0 because I'm using the concept of principal directions here. So everything is set up. I can go ahead and run this simulation, and I can observe the results. So this is the result of subsidence at the end. I'm looking at subsidence from geomechanics, and going forward in time, you can see it's increasing with time. But I'm looking at 3D, so maybe it's not the best view to look at. But anyways, it shows you that the maximum subsidence in this case is around 3.2 millimeters, and the value is positive. Let me go and look at a 2D view now. Oh, it's right here. And let me also look at how porosity changes with geomechanics. So initially, this is your porosity distribution in the planes where the wells are located. And you can see how it is changing with the changing geomechanics. And you have many other geomechanical properties that you can look at. You can look at things like effective mean stress or something else. So you can see effective mean stress initially was around 9,000 kilopascals, and by the end it is about 10,000 around the wells. So that's all good, but it's giving me the answers in the region where reservoir is present. So if I want to know what happens at the surface, I'm not getting the answer for that. I'm only getting the answer for what happens at the top of the reservoir, which is about 510 meters from the surface. So how do I incorporate the surface now? I need to use the dual grid system. And in this example here, I'm setting up the dual grid system in the same reservoir. So all these keywords here, which I've highlighted, they deal with the creation of a geogrid, which is our dual grid system. And I've set up the type of the grid as Cartesian. I've specified the dimensions of the grid, the thicknesses of various regions, and I have translated this Cartesian grid to overlap the entire reservoir. And then I'm using 2 geomechanical rock types now. Rock type number 1 will be used in the region where actual flow simulation is happening, and rock type number 2 will be used in the region where we have only overburden. And I have changed all the stresses to represent things correctly all the way to the surface. And let's look at the results from this one now. Now this one shows me results all the way to the surface. As you can see, the Z or the vertical dimension is starting at 0. Now we can look at effective stress in any plane we want. We are looking at the last plane, but we can look at any other plane. You can see that the region where the reservoir is present, which is around 500 meters deep, I'm using a very refined geomechanical grid on the left side. On the right side, we are seeing the corresponding reservoir picture. And we can go forward in time and see what happens. So all this reservoir grid is being mapped here in the geomechanics as well, and then it's propagating all the way to the surface. One of the questions which people generally have is what kind of subsidence or heave I'll see at the surface. So let's see that as well. Let me plot subsidence from geomechanics. So the reservoir simulation gives you the impression that you have about 5 centimeters of heave at the top of your reservoir, which is correct, but only at the depth of 500 meters. When you take it all the way to the surface, the amount of this heave is only about 2.3 centimeters. So a lot of the heave is absorbed by the overburden. So that kind of answers you can get only when using dual grid system. And it's really, really useful because you really want to know what happens at the surface without taking too long to run your simulations. So that's my last comment on my demo. And let me go back to slides. The next concept I want to introduce is the concept of geomechanical post-processing. Now, in some cases, you may not run geomechanics because maybe you were not aware about it or something like that. You can still use geomechanics. You can still run geomechanics without rerunning your flow simulation, as long as you have the restart results. And that's what geomechanical post-processing is about. It allows you to run the flow model alone without considering any geomechanics, and later on adding geomechanics and changing geomechanics in whatever way you want without the need to rerun the flow model. Geomechanics can continue to use the pressure and temperature from your reservoir simulation and just run geomechanical part very quickly in a one-way coupled mode. By doing that, it reduces the compute time for many, many runs where you only need the effect of geomechanical parameters on something. The workflow for that particular feature, it works like this. You have your flow model with the restart outputs but without any geomechanics, and you have run it in gem or stars and obtained reservoir results. Then you can go ahead and add geomechanics and add a keyword, GeoPostPro, and run the restarted run in gem or stars. By doing that, you continue to have your old reservoir results, but you also get additional one-way coupled geomechanical results. And this is very useful because it gives you the idea of how important geomechanics is without really running the simulations for weeks and weeks.
Before Varun goes on to the case studies, I'd like to pose a question to our attendees. A question will pop up on your screen, and the question is, were you aware that you can use geomechanics in your reservoir models to study caprock integrity? And you can respond by clicking on one of those options. The options are yes, no, and yes, but I wasn't aware that I could do it using stars and gem. Let's give a few seconds here, and responses have started to come in. It's a bit of a mixed response here. 52% of the attendees actually have responded yes, that they are aware of this feature. 23% no, and around 26% say yes, but I wasn't aware that I could do it in stars and gem. So it's a mixed response, and hopefully today's webinar will help you understand some of the mechanisms and features and capabilities that are available in CMG simulators to enable you to model some of the geomechanical effects, because geomechanical modeling and caprock integrity studies have become a routine in especially thermal processes. So I hope you all will find this webinar really useful in that respect. Back to you, Varun.
Okay, thank you everyone for your responses. It's very good to see that many people are actually aware of the feature of using stars and gem for doing caprock integrity studies. And we'll talk about some of our published examples. So the first one here is the caprock integrity study for SAGD operations, which we presented last year at the Heavy Oil Conference, and the paper number is at the bottom here. The concept is that in any SAGD operation, you have two main objectives. One is to maximize the profit by maximizing the net present value or minimizing the steam oil ratio and things like that. But the other objective is to ensure operational safety, which means you don't want to have any caprock failure and you want to avoid high heaves. A schematic on the left side here shows you what happens in a typical SAGD operation. So the yellow color is the steam chamber, which is growing with time, and it starts to bend the caprock. And in some cases, this caprock can break and steam can be released to the upper formations. And the result of that can be disastrous, especially if you consider this example on the right-hand side in the Jocelyn Creek project, where steam actually escaped and caused a widespread destruction on the surface. So none of us wants that to happen to our projects, which means we need to ensure that all our operating parameters are such that they will not cause the caprock integrity failure. So we in this particular study, we developed a workflow to do that. So what you do is you develop a base case with two-way coupled geomechanics and compare the model's results with field data, both in terms of rates, which is the reservoir side, and in terms of heaves, which is the geomechanical side. Then you analyze the operating parameters, do some sensitivity analysis, and try to find out what parameters affect profit and what parameters are affecting your safety. Then you develop optimum operating strategies based on your observations. And once you have that, then you test these optimum operating strategies under geological uncertainty. So we used a simple example we used a 2D model which represented an element of symmetry, and it represented 1/20th of the well model. And in this particular case, we had 3 different layers. The sand was a homogeneous, good quality sand. The mudstone was heterogeneous. It was better quality near the sand and worse quality near the shale. And then at the top, we have the shale caprock. In terms of geomechanics, the rich sand, the actual pay zone, was modeled as nonlinear elastic, and the response for its stresses versus strain is shown on the picture on the left-hand side. The mudstone, the shale, and the overburden were modeled as linear elastoplastic, each with different properties in terms of Young's modulus, Poisson's ratio, and cohesions. On the right-hand side, I'm showing you the different stresses, the 2 horizontal stresses and the vertical stress with depth in 2 pictures. The top picture is showing you the distribution of stress in the deeper reservoir, which is 300 meter deep. And we ran another case with shallower reservoir, which was 150 meters deep. And for both of them, we summarize our observations, which you will see in the next few slides. How to identify the caprock failure? So we try to identify that using 2 different objective functions. One was the heave at surface and at the top of shale layer, and one was the time taken for caprock failure to initiate, which was identified by using 2 properties called yield state and safety factor. Safety factor is shown on the right-hand side, and we can discuss about it more outside this webinar. Then on the other side, we also have another objective function for the profit, and profit was measured by subtracting the steam injection cost from the oil revenue. The different parameters that we altered were injection pressure and temperature, well pair spacing in the lateral direction, and the injector-producer separation in the vertical direction. And these are the results of the base case. The top 2 pictures are showing you the reservoir simulation results, just the reservoir properties in terms of temperature and gas saturation. And the bottom 2 pictures are showing you results from geomechanics. So if you are not familiar with SAGD, the red color which you see here indicates the presence of steam chamber. The red zone is the hottest zone. And the same thing you can see on the right side in terms of gas saturation. The gas is steam as well as a solution gas. In the bottom, you can see the safety factor on the left. And you can see its value is ranging from 1.1 all the way to 10. So a value of more than 1 indicates that the failure in that particular rock hasn't happened yet. A value of 1 means the failure has happened. So right now, the failure hasn't happened anywhere in this particular case. Now, failure happening in the reservoir region is not bad because it increases reservoir permeability and porosity and causes dilation. What we don't want to see is the failure inside the caprock. So that's what we'll study about. And then we can also see on the right-hand side bottom, we are showing displacement along the vertical direction. So around the region of the caprock, we are seeing about 18 centimeters of heaving. And at the top of the formation, on the top of the reservoir, we are seeing the surface heave of about 13 to 14 centimeters. Now we ran some sensitivities where we varied injection bottom hole pressure, temperature, the well spacings, and the location of the injector. And what we found is that the parameter that had the maximum impact on net present value was the injector. And it was injector BHP. And what we see is that as you increase the bottom hole pressure of the injector, you see a higher net present value. So that's the main gist of this slide. And for doing this study, we use the CMOST tool. But on the other side, if you compare the parameter sensitivities on surface heave, you see that the injection BHP also impacts the heave. So by injecting at higher pressure, you see a higher net present value. But you also experience higher amounts of heaves, both in the case of shallow reservoir as well as for the deeper reservoir. So that poses us a question, should we go for a higher injection BHP or a lower injection BHP? And that is the optimization problem that we try to solve here. So a quick example of the effect of injection pressure. 2 cases, model A and B, where everything is almost the same. The only difference is the injection BHP is slightly higher in the case of model number A. And you can see here, in case of model number A, in the shale zone, you see the red color indicating the yield state of 1, and that indicates plastic failure. In case of model B, there is no failure in the caprock. So model A is obviously doing a better job in increasing your NPV slightly, but at the same time, it's causing the caprock failure. In looking at the safety factor with time, we see at about 2,500 days, the safety factor of model A goes down to 1, and that means failure. So that poses the question that what is the maximum operating pressure that you would choose in this case? The answer would be 5,090 kPa. Then we did some optimization where we tried to maximize the NPV on the y-axis and maximize the time taken for caprock to fail on the x-axis. And the green points here are the optimized points. If you touch 3,650 days, that's 10 years of simulation time. That's the maximum I ran for. So this means there is no failure. Anything less than that means there is a failure at some point in time. So while there are some models in red color which had a higher NPV, they also had the case when the caprock failed. Whereas in those green models, they were optimum, where we had maximum NPV with minimum failure. So the results were like this. For the shallow reservoir, we found that the maximum operating pressure should be about 2,800 kPa, and for the deep reservoir, it should be about 5,000 kPa. Now, using these parameters and taking them forward, we also have to address the issue of uncertainty. There is an uncertainty in geomechanical properties, and we ran several cases with the changing values of geomechanical parameters. And what we found is that the heave is showing a big distribution. In some cases, you may see that the heave is about 40 centimeters, but in some cases, while changing these properties, it may increase to 50, 55 centimeters in the case of shallow reservoir, and the similar experiences we had for the deep reservoir as well. That tells you that even though you have optimized your case, it may still not be completely safe considering there is an uncertainty in all the properties. So that was our first uncertainty assessment. We ran another one where we changed the geological properties, where we took a poorer quality geobody and distributed it all along the reservoir. And I have an example here, comparison between 0% poor geobody and 10% poor geobody. And we see that the steam chamber growth is very similar in both cases. In both cases, the injection bottom hole pressure is higher than the maximum operating pressure. So while it seems like the performance is similar in both cases, the performance in terms of caprock failure is quite different. When we have a clean sand, the steam chamber growth is higher, slightly higher, and that causes the caprock failure. Whereas when we have poorer quality sand, the caprock failure hasn't happened yet. So a recap of what we saw in this case study is that SAGD optimization is a problem of NPV maximization with a constraint that you need to maintain operational safety. And we present a workflow for that. We found that the operating pressure was the most important parameter for this, and that under geological uncertainty, even the projects which you think are safe may not be quite safe, and that the poorer quality reservoir rock may lead to a higher MOP. Now that brings me to the second case study where we do another caprock integrity study, but this time to mitigate risk in a CO2 storage project, and we presented this at the ATCE a few years ago. The paper number is at the bottom. In a CO2 sequestration or CO2 storage project, you inject CO2 into a saline aquifer where CO2 can be stored by 3 different processes. It can dissolve in the water, it can undergo ionic reactions, or it can undergo mineralization reactions. But it can also escape through the caprock, and if it escapes, that's a failure for you. So to model the failure of caprock, we used a model called Barton-Bandis model. We modeled the caprock as naturally fractured, but the fractures were initially closed, and they were closed because there is a normal stress acting along perpendicular to them. Now when you inject any fluid here, that increases pressure and reduces the effective stress. So on the right side I have a picture of permeability on the y-axis and normal effective stress on the x-axis. So when you inject any fluid, the normal effective stress goes down, and at a certain point it goes down so much that the fracture can suddenly open up and permeability will be increased. And after that, even if you start producing from it and increasing the normal stress, the fracture cannot completely close, which you can see here. So we use this model, and for the reservoir side we use a simple model again. it had an aquifer, which is shown in green color here, and two overburdens, number 1 and 2, shown in red and yellow respectively. And there were two caprocks shown in the blue color here. And what we saw was that when you are not using geomechanics, it seems like that all the gas you inject is staying in the aquifer and your project seems successful. But when you use geomechanics, then this gas, you find out that this gas is actually escaping to the overburden, which means the project is no longer successful. To analyze this further, to see why this happens, you can see the picture on the left side. The red color is showing fracture probability here. So it's 0 till about 2002, and then suddenly fracture probability increases. And that corresponds with the decrease in the normal stress and the increase in the fracture pressure. This happens at about 2 years, which is shown on the right-hand side. This caprock, its permeability increases suddenly after 2 years. Then the CO2 continues to escape through it, reaches the upper caprock, and fails the upper one after 4 years. And after 10 years, you can see the gas saturation is all over the place. It's not just in the aquifer, but it's expanded all the way to the overburden. So we know that this failure can happen. Now, how can we mitigate the risk? So we did two studies. We studied the effect of rate and the effect of the injection temperature. We found that when you inject at lower rate, the surface heaves that you obtain are lower than when you inject at a higher rate. We also found that when you inject at a lower temperature, which is at the bottom picture on the right-hand side here. So when you're injecting at a lower temperature, you're on the blue line here, and the effective stress, which is on the left-hand side axis, it's reducing, but it takes a longer time to reduce to the value of 0. So that happens when you're using a lower temperature injection. As you increase the temperature of injection, this failure or this reduction in effective stress happens much faster. So what we found in this particular study is that tensile fractures can be observed when the caprock starts to bend. And we can model it using Barton-Bandis model. In this case, we used it for CO2 sequestration. We can minimize and avoid caprock failure by injecting at lower rates, and we can delay the caprock failure by injecting at lower temperatures. And now that brings me to my last case study for today, and it's a slight change of topic. It's no longer caprock integrity, but we are going to see the effect of geomechanics, or the importance of geomechanics in history matching 4D seismic data. This was also a SPE paper we presented last year in the Heavy Oil Conference. So 4D seismic surveys are just 3D seismics in time. These are used nowadays quite routinely in SAGD projects to understand the well conformance better, to get some insights into reservoir flow mechanics, and to safely drill new infill wells. And you can also get some qualitative comparison of 4D seismic with simulation runs. The main idea is to understand where the steam chamber is by running these 4D seismic differences. So on this slide, you are seeing a 4D seismic in a project at different points in time. The colors you see here are the positions of steam chambers at different times. So if we assume that these colors are showing the correct position of steam chamber, that poses a question to us, that why do we see these isolated pockets? The problem is that steam cannot be isolated in one place. It must be some seismic property or some geomechanical property which we are seeing here, not just the presence of steam. So we need to understand what we are seeing in 4D seismic to be able to history match it using reservoir simulation. So understanding of 4D seismic data is quite important. We need to understand what it shows. Is it a temperature? Is it a heated zone or a gas saturation? Or is it some seismic property like shear velocity or acoustic impedance? And one important question is, can we use temperature as a simple proxy for seismic attributes? And another question is, do we need to include dynamic geomechanical calculations? The picture on the right side is another study which we did for a client here, and the reference is shown on the left side here. What you see in this picture is 4D seismic data shown in the dark red color, the simulation steam chamber shown in the very light color, and the intermediate color is the overlap of these two data, which means where we were able to get a history match between the simulation steam chamber and the 4D seismic steam chamber. And we were using just temperature cutoff to identify the presence of steam chamber. And you can see after a number of iterations, we get closer to the actual history data, but it's not a perfect match. And the reason is we don't really know what flow property should we associate the 4D seismic to? And we tried to answer this question, and we thought that maybe acoustic properties are what we see on seismic rather than the flow properties. And we did some calculations to compute the values of compressional wave velocity, shear wave velocity, and acoustic impedance using the equation on the right-hand side. We also took a major effect in consideration, which was the fact that the bitumen can change from the solid to liquid in the 10 degrees to 50 degrees Celsius range. And we set up simple cases. This is one of the cases which we set up, where we have 3 distinct zones. We have the Caprock. We have the Caprock is in the dark blue color. Then there is mudstone, and then there is a clean sand with some intermediate, with some shale lenses. And at the bottom again there is a shale. So we ran a few cases. This is one of them, and the results of one of the cases is shown on this slide. At the top you are seeing the temperature distribution. In the middle you are seeing the actual shear wave velocity while considering changing geomechanical properties with time. And at the bottom you are seeing the values of shear wave velocity again, but this time with constant geomechanical properties and non-coupled simulation. And what you see is, if you consider temperature as the sole criteria of the existence of steam chamber, then it would appear to you that from the first picture that the steam chamber is growing a lot vertically and lot less horizontally. Whereas when you see the actual shear wave velocity, you'll see that the steam chamber does not grow as much vertically, and it has a lot more features to it, features which look similar to what we saw in the pictures earlier. So it gives you an idea that maybe shear wave velocity is something which we should look at, and considering dynamic geomechanics to answer questions about 4D seismic history match. The bottom picture also shows you that the steam chamber is not growing vertically so much, but it doesn't have all those features which the dynamic geomechanics case has. Another example where the shale lenses and the continuous shale is right on top of the injector well. So here also you see that the temperature is extending far beyond the shale lens and going a lot more vertically, whereas you see more features on the shear wave velocity picture considering geomechanics, and you see a lot more extent on the lateral direction in both these examples from top and bottom. So what we see in this particular case study is that there is a lack of clarity regarding what flow property does the 4D seismic differences relate to. And there is always a need to have a discussion between the reservoir engineer and the geophysicist to find out what properties that should be considered. We also found that geomechanical properties are important, and their effects are important, and that geomechanics can help close this gap which is existing currently between the 4D seismic creation and the reservoir simulation steam chamber. With that, I'll end my presentation with these concluding remarks. What we saw in this presentation today is that coupled geomechanical modeling can complement reservoir simulation, and you can achieve optimum production and also ensure the safe operations at the same time. We presented that you can predict compaction and heave from your reservoir simulation. You can ensure Caprock integrity, and you can get some help in 4D seismic history matching. CMG provides an excellent tool. We have a really good tool and with very advanced features which you can use for running your geomechanical simulations, and we did a demo on that as well. The advanced features of CMG's geomechanics include dual grids, geomechanical post-processing, fracture initiation models, and a lot more, which are too many to be discussed in this presentation. But if you send us your questions, we will be happy to answer them. And with that, I invite any questions that you may have.
Thank you, Varun. We'll now take up any questions that you may have. If you haven't submitted your questions, you can do so now using the chat window on your screen. There are a couple of questions already we have received, so I'll try to take them one by one. The first question is from Ehsan Ali, and the question is, which version of IMEX has geomechanics and dual grid available?
Thank you, Ehsan, for the question. IMEX currently does not have geomechanics. We only have it available for stars and gem, just because we didn't have the business need for that yet. And as far as the dual grid is concerned, it's available in both stars and gem, and it's available, I believe, in all the versions since 2011.
The next question is from M. Edwards, and the question is, overburden parameters must be uniform all the way up to the column, or can you have multiple rock types?
So good question. We can have multiple rock types in overburden. You can have any kind of distribution you want, just like you would have in a regular reservoir simulation. You populate the facies. The same way you can have geomechanical facies populated all over the place.
So the next question is from Mohammed, and the question is the Cmg geomechanical package capable to handle elastoplastic behavior?
So that's an easy question. Yes is the answer. And the models available in Cmg's constitutive model list, you can go over them and you'll find out that they are elastoplastic.
So the next question is from Kodai Kato, and the question is, I like to couple with other companies' geomechanical simulator. The image is geomechanical simulation using this, then export the results into stars. After flow simulation using stars is done, then back into the geomechanical simulator. Can I realize this loop using CMOST? Geomechanics simulator is not GoCAD.
So I understand, Kodai, that you are asking about coupling geomechanics using a third-party simulator. So that can be done. We have a feature which was introduced last year. It's called Outboard. So I'd encourage you to look in our manual about Outboard feature, and using that you can export the pressure temperature to the third-party simulator and take the properties back into CMG simulator.
So both the geomechanics simulator and stars run concurrently, exchanging information between the two simulators. So the next question is from Walid, and the question is, have you guys dealt with coupled WAG geomechanics studies?
Thanks for the question, Walid. I haven't done any coupled simulations for WAG, but I can get more information if anyone else has done that and let you know through email later on.
The next question is from Z. The question is, for the two-way coupling, is it coupled every single time step or every several time steps?
So the answer is that it's coupled every single time step. So within a time step, you keep on going back and forth between geomechanics and reservoir until the time step convergence has reached.
The next question is from Pingui, and the question is, for the geomechanics post-processing feature, how does the coupling work without rerun of the flow model? Is this just a geomechanical calculation kind of honoring the flow results?
So Ping, I think you have got that right already. It's using the existing reservoir results and just running geomechanical simulations in a one-way coupled mode, so your reservoir results are not impacted, but you get a prediction of the geomechanical properties.
The next question is from Shraddha Vishwanathan, and the question is, does the grids have to be structured?
Yes, Shraddha, the grids have to be structured. We don't support unstructured grid in CMG, but you have flexibility to use any of the grid types available in CMG for geomechanical simulations.
The next question is from Rashid Sohail, and the question is, can the geomechanics be used to examine fracture growth in tight reservoirs?
So the fracture growth can be, we can model that. We have different ways to do that. Currently we have a feature where we can import the fracture properties generated in a software like GoCAD, sorry, not GoCAD, Gopher, and we can bring that into CMG, and that will let you honor the actual geomechanical properties to create the fractures. But we can also use CMG's geomechanics to predict fracture growth. So if you want to talk more about that, you can drop me an email.
The next question is from Roman, and he'd like to know is how permeability is changed by effective stress. What kind of measurements do you need to include from the lab?
Okay, good question, Roman. The permeability is coupled with the change in effective stress. So there is a bunch of ways we can do that in CMG software. One of them you saw, the Barton-Bandis model. There's another way which uses research done by University of Alberta in the late 90s, and that's done in Rick Charlatonic's group, and that relates the permeability to the volumetric strain. And you can look up their work on that. You need to do some experiments for getting that kind of data, though.
The next question is from Bakul Mathur, and the question is, can geomechanical modeling in CMG model the wormhole propagation in the heavy oil reservoir due to sand production? Is it in terms of increase in permeability?
So we haven't done this kind of study yet. We can model this substantial increase in permeability with geomechanics, but for wormhole we also need to have solid flow. So maybe you can talk to us through email.
There is, just to add to that, there is a wormhole modeling module inside STARS. It was developed by Alberta Research Council, now Alberta Innovates, and it's available in STARS, where you need to model solid propagation inside the reservoir, leading to wormhole development and growth. So if you need more information on that, we'll be more than happy to send it to you at a later stage. The next question is from Xiao Dan Ma. The question is, besides of SAGD cases, could you give any case examples of hydraulic fracture, DFN models, and CMG coupling with geomechanic features and functions?
So again, it's similar to Rashid's question earlier. We are working on that. We are trying to generate some case studies on that, but we haven't done anything which is published yet.
Okay, the next one is from Shivam Agrawal, and the question is, what are the various options for flow geomechanics coupling? You showed 0 to 3 options in the GUI interface.
So just to mention that, number 0 stands for one-way coupling. The numbers 1, 2, and 3 are all different kinds of two-way coupling. The only difference between the numbers 1, 2, and 3 is the actual formula through which the porosity is calculated.
The next question is from Mariam, and the question is, what are the permeability stress correlations?
So it's similar to the previous question. The permeability is related to effective strain through one of the correlations done by University of Alberta in the late 90s. And there are other ways to couple, to relate the permeability to the effective stresses through tables.
The next question is from Mahmood, and the question is, what are the boundary conditions when we solve for geomechanics?
So the default boundary conditions are your edges, the right and left side edges are fixed, and the bottom is fixed as well. Only the top is free to move. That's a default boundary condition, but you can change the boundary conditions as well.
The next question is again from Shraddha, and the question is, can you give us an estimate of CPU time for a fully coupled simulation for your SAGD case study?
We haven't done any benchmarking, but there is a bottleneck in geomechanics. Currently, the geomechanics is not parallelized. So while we run the reservoir simulation time step in parallel, the geomechanics time step goes in serial. We are working to make it parallel right now.
The question is from Vinicius, and the question is, how important must be the impact on the criteria to consider two-way coupling rather than one-way coupling?
So I'll give you an example. When you run geomechanics, you will see changes in porosity and permeability. Depending upon how big these changes are, you can see a big change in the oil production rate. So let's say your oil production rate changes by 5%. That's a huge amount. And in that case, your two-way coupling is more important. So then you need to identify that running geomechanics and seeing how big the changes are in porosity and permeability with time in a one-way coupled situation, and then move to two-way coupled.
The next question I'd like to take is from Charles Hager, and he'd like to know is, are there any special handling needs for a salt formation?
As long as you can define the properties of the salt properly, you don't have to have any other special handling needs. So you just have to make sure that all the properties in terms of Young's modulus, Poisson's ratio, and so on are defined correctly, and you are using the correct constitutive models. I don't think you can use the general Moore-Coulomb model there. So as long as you can use a correct model there, you don't need a special any other special thing there.
The next question is from Kata Kyrgyz, and the question is, what does a 10% poor geobody mean in your example?
Okay, so that was the case study number 1. In that case study, we distributed a poorer rock type in the reservoir, and we did several runs. Sometimes we didn't distribute it. Sometimes we used a volume fraction of 5% of the poorer geobody, and sometimes we used a volume fraction of 10% of the poorer geobody. And poorer geobody just means a poorer value of permeability, porosity, and relative permeability. So it's just like a interdispersed shale in the actual sand.
The next question is from Jan Legallo, and the question is, how do you define the Caprock failure model? Do you extend it throughout the overburden?
Yep. So in our first case study, which talks about the Caprock failure studies, that's where we actually extended the reservoir all the way to the surface. However, you don't have to do that. You have the option to use the dual grid system, but in this case, I wanted to use the exact distribution of the rock types which are in the reservoir in the geomechanical grid as well, and that's why I actually extended my reservoir grid all the way to the surface and then modeled the Caprock integrity.
The next question is from Edgar Castillo, and the question is, can you use geomechanics post-processing with dual grid?
Yes, you can use the geomechanical post-processing with dual grid. So imagine you can have 1,000,000 grid blocks in the reservoir simulation which runs for a number of years. You can reduce the geomechanical simulation to model just 10,000 blocks or less than that using dual grid system and model all the way to the surface to get estimates of surface heaves.
The next question is from Guido, and the question is, has this geomechanical coupling helped matching steam injection pressures in cyclic steam injection when usually simulating pressure is higher than the real reservoir pressure?
We haven't done any projects internally, but I believe our clients have done some projects where they have used geomechanics to match the actual steam injection pressures. I can get you more information on that later on.
The next question is from Bertrand, and the question is it possible to have anisotropic material? What I mean, I think you mean is that can you have directional geomechanical properties defined?
Yeah, so thank you for the question, Bertrand. Right now, our properties like Young's modulus and Poisson's ratio, they are not anisotropic. They are the same in all directions. The stresses are obviously anisotropic, but the other geomechanical properties are not yet.
The next question is from Colin Cranfield, and the question is, when and in what situations is it recommended to use gem versus stars when doing coupled geomechanical flow modeling?
Okay, so that relates to what you want to do in flow simulation. If you want to model things like mineral reactions, you need to use gem. If you want to use things like polymer flooding or steam injection, you need to use stars. Geomechanical features are absolutely identical in both stars and gems, so that part is not affecting your decision of which simulator you should use.
Okay, for the sake of time, there are several questions that I see, and it's still the questions are pouring in. At the moment, for the sake of time, we will have to stop here, but hopefully we will get back to you in the next 24 hours with your questions if we were unable to take your questions right now. I hope you have gained a better understanding of some of the concepts related to geomechanics and various features and capabilities available in the CMG simulators. CMG does offer a multitude of training courses for all skill levels. For those of you who are interested in knowing more about the geomechanics modeling, we do offer a 2-day course on geomechanics modeling using CMG. We also offer several company-specific customized courses on a variety of other subjects all around the world. For more information on our training course offerings, I'll invite you to visit our website at www.cmgl.ca. We will be posting the recorded version of today's webinar on our website within the next 24 hours. Please log in using your CMGL username and a password to access the material. In addition, as I said, if your questions wasn't answered during the Q&A session today, we will follow up with you within the next few days. If you have any other questions related to the materials presented today or would like to know more about our product offerings, please do not hesitate to contact us at sales@cmgl.ca.